3.3 Properties of Determinants. You see the homework assignment there on the page. So this will be quick. For A and B, both n by n square matrices, same size. The determinant of A times B is the determinant of A. By the way, this comes in real handy. Times the determinant of B. For any scalar, remember a scalar is just a number that's multiplying a real number. Except I can't spell. Sorry. You didn't see that. For any scalar C, the determinant of the scalar multiple of a matrix is just the scalar times the determinant of the matrix. Oh, sorry, it's an n by n matrix, and every entry in that matrix gets multiplied by C when you multiply by the scalar. So when you do the determinant, you're obviously going to get C n times because there's n rows and n columns. Okay, next, if the matrix A is invertible, and we've already learned how to find the inverse. So if it's invertible, then, by the way, the notation, straight up bars like this, if it's invertible, then its determinant is not 0, okay? You're going to get a determinant of 0 for lots of different reasons. If you have a row or a column that ends up being all zeros, or could be reduced to all zeros using basic row operations, then your determinant would be 0. But there are other matrices that have not that many zeros in them, but they end up having a determinant that's equal to 0, which means you can't find the inverse. And another thing, the determinant of the inverse, because we said A is invertible, is 1 over. It's the reciprocal of the determinant of A. Okay? I know I mixed up the notation there, but I'll deal with it. Next, the determinant of A equals the determinant of the transpose of A. And based on all of these things, if you put this stuff together, you get cool stuff like the determinant of A times its transpose is the same as the determinant of A times A. Why? Hold the phone. Let's write this like this. Remember, the determinant of AB is the determinant of A times the determinant of B. So if I have A times A transpose, then it's the determinant of A times the determinant of A transpose. But the determinant of A is the determinant of A transpose. Therefore, I can just multiply A times A and get the same thing, right? But also, this equals the determinant of A squared. Why? Because the determinant of the product, A times A, is the determinant of A times the determinant, in this case, of A. So you're just finding the determinant and squaring the answer. When will you use that? I have no idea, but it's kind of cool. Another note here, I'm going to keep shrinking this so that I can fit everything on one page. It's just that kind of section. Note. If you haven't noticed yet, your textbook, the author likes to say, this is the way it is, it's always this way, end of story. And then he'll put a footnote or a note in the margin or something at the bottom of the page that says, well, you know, sometimes you can do this, or sometimes you can't do this. So read your book, look at the examples in the book, and make sure that you read all the stuff in the margins and at the bottom. But this is just my note. If A is singular, what does singular mean? If A is singular, then A equals some matrix with an entire row or column of zeros. Okay, so that's the definition of singular. And if A is an n by n matrix and we're finding the determinant, and the determinant is not 0, and this is based on what we said earlier, then A is invertible. And you can use the inverse A to solve and because you can do it with the inverse, this has a unique solution. So if you are planning to solve a system of equations and A is the coefficient matrix, then you can find the determinant of A to check and see if a unique solution even exists. If your determinant is 0, then it means you have an entire row or column of zeros, and you're going to have infinitely many solutions or something like that. So when I have a big system that I need to solve, I'll very quickly do the determinant and know whether I need to keep going or not, know whether it's going to have a unique solution. And based on what I just said, we're going to go straight into 3.3. Sorry, 3.4. We were just in 3.3. The only thing that we're going to do in 3.4 is Cramer's rule. This was not in your in the course outline, but I think it's too important to not study. When you are in differential equations, you'll be using Cramer's rule to solve certain types of problems. It's not presented as Cramer's rule. You're just doing this weird stuff. If you haven't studied what a determinant is, you don't realize you're doing a determinant. And it just seems like you're randomly putting things in and multiplying junk out and subtracting. But when you get there, if you've had this class, then you'll recognize that you're just solving a system of equations using Cramer's rule. And the best way to do Cramer's rule is just to do it. So let's say I have a system of n equations with n variables. So I've got an n by n system. of equations, and I need to solve, and I look at it in terms of a matrix equation, then there's x1 is going to be the ratio of just the coefficient matrix in the denominator, the determinant. And in the numerator, where if you're solving for the x's in the first column, then you're going to take that first column and replace the x's with the b's. So b row 2, dot, 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 until you get to the nth row. And you're going to still have the a's all the way out to the nth column. And all of this until you have a, n here. So what you're going to do, if you're solving for this, you're going to replace that column with this. The denominator is always just the a coefficient. So whatever row you're solving for, you replace with b. So if I was doing x2, it would be the second column that got replaced. All right? So, and you keep on going that way. So let's do an example that makes it easier. I'll just start with a 2 by 2. 2x1 minus 3x2 equals minus 7, and minus 4x1 plus x2 equals 5. So solving for x1, I have the ratio of the determinant of the coefficient matrix on the bottom. And on the top, I'm going to replace the x1 coefficients with the b part. So this is minus 7 and 5. Everything else stays the same. All right, so let's calculate this out here. First, the coefficients in the bottom. I have multiplying down this way, I get a 2. Subtract multiplying up, and I see that my denominator is negative 10. That will be the denominator for both, for the whole rest of the problem. In the numerator, I'm going to multiply down and get negative 7. Subtract multiplying up, where I got negative 15. So negative 7 plus 15 gives me 8. And I get that x1 is equal to negative 4/5. All right, x2 ratio. I already found the bottom. The top, x1 coefficients stay the same, but x2's coefficients get replaced. My bottom's minus 10. The top is going to be 10 minus 28. I'm going to get negative 18 over negative 10, which is going to be positive 9/5. All right, so the solution here to this system is x1 equals minus 4/5 and x2 equals 9/5. That was pretty easy and straightforward, right? All right, let's try a nasty old 3 by 3. Okay, let's say we have Okay, so some people like to start out just doing the coefficient matrix, getting that determinant done. I don't have any zeros, so expanding would be ew. So I'm going to use my shadow method here, copying column 1 and column 2 off to the side. So now when I multiply this out, I'm going to multiply, let me get a yellow here. I'm going to multiply this diagonal, this one, and this one, and add those answers. And I'm going to get 9 minus 8 minus 4. Subtract, I'm going to go up this way, here, and here. And that's going to give me a 1 plus 12 plus 24. Okay, that gives me -3 minus 37 equals -40. So that's going to be my denominator. When I have x1, I have -40 in the bottom. The x1 column gets replaced with the b column. Everything else stays the same. 4, 1, 2, -1, 2, and 3. Again, I'm going to cheat and copy column 1. Make sure you do these in order. And column 2. And multiply down and over. So I get a 3, and 4 times 4 is 16, twice 16 is 32, and a minus times a minus is a plus 6. Now starting at the bottom and going up, I get -4, +4, and -36. This is going to give me 41 minus a -36 over -40. Who made up this problem? This is awful. 77 over 40. And we'll have to just check this when we're done. x2. The first column stays the same. Second column gets replaced with b. Third column stays the same. The bottom is -40. All right, shadowing 3, 2, -1, 1 minus 3, 4, and I'm going to get going down 3 times 3 times 3, and it's -27, a -2, and a -8. Now subtract going up, -3, 4 times 2 times 3 is 24, 3 times 2, and I'm going to get -37 minus 30 minus 3 is 27. -64 over 40, -40, which is, let's see, 4 goes into both. I can reduce that more. 8/5 positive. All right, and that's x2. And I'm running out of room for x3. Let's do this. Column 1 stays the same. I'm going to shadow in blue. Oh, what did I do wrong? Did you catch it? Made a mistake. I'm solving for x3. So the third column gets replaced with the b values. Now I'm going to shadow the first 2 columns and multiply all over -40. And I'm going to multiply down and get 12 plus 12 plus 4 minus -1, -18, positive 16 twice is 32. Which is going to give me 28 minus 32 minus 19 is 13. And I'm going to get a 15/40 positive over negative, so it's -3/8. And then you have to check your answer.